Okay, so for the learning outcomes, at the end of this topic, you should be able to write the formula of pure bending and flexural theory. Okay, then the second one is to identify the plane of symmetry. Okay, the third one is to apply the flexural formula in bending for determinate beam problems. Okay, and also to produce the shearing stress distribution diagram for the given problem. Okay, so we move on to the bending stress. So when a beam is subjected to load, the beam actually will deflect downwards, right? So if the load is from the top, okay, so therefore it is acting downwards. So therefore what happens to our beam is that it will deflect downwards as well. Okay, so if we have this case, okay, therefore we will have two different zones. Okay, so the top part will be subjected to compression and the bottom part will be subjected to tension, right? So this is the undeformed beam and this is the beam after the deformation, right? So this is the normal or typical behavior of a beam, okay, under loadings, okay. Right, so this actually can also be determined, okay, when we determine the bending moment diagram, right? So with the bending moment diagram, okay, when we have a positive bending moment, as what I have already explained earlier, right? So if we are considering that the positive bending moment is at the bottom of the beam, okay, so therefore we are going to consider that it is under tension at the bottom and it will be under compression on top, right? So as you can see here, we can also draw the stress block diagram, okay, for our beam, okay, whereas we are going to have sigma compression, okay, on top, and we are going to have sigma T, okay, or sigma for tension at the bottom, right? So this is for a typical uh, deflected beam, right? So this is the values, okay, that we are going to actually determine, okay, in the bending stress analysis. And now we move on to the assumptions, okay, in the theory of simple bending. Okay, so the first one is that the material of the beam is perfectly homogeneous and isotropic, right? So if we are dealing with a steel beam, okay, or we are dealing with a concrete beam, okay, so therefore we are going to consider that the material is homogeneous and isotropic throughout the dimension. Okay, then the second one is that the value E is the same in tension and compression. Okay, so this E is the Young's modulus. Okay, then the third one is the beam obeys the Hooke's law. Okay, as what we have already learned previously. Okay, on this Hooke's law, which is considering the modulus of elasticity as well as for the strain, the stress and also the strain. Okay, and then as for the fourth one, okay, is that each layer of beam is forced to expand or contract independent of the layer above or below it, right? So this is for the layers of the beam. Okay, so then we move on to the Flagship formula, right? So in the calculation of the beam stress, okay, we are going to use this formula, okay, which is sigma equals to my over I, right? So the sigma is the normal stress, okay, or the bending stress that we wanted to determine. Okay, then as for this m, this is the bending moment value, right? So this bending moment value can be obtained from the bending moment diagram, right? So we have to search in particular, okay, for the part, okay, whereas we wanted to determine the bending stress, okay, then from there, okay, we can determine the value of the bending moment, okay, from the bending moment diagram. Okay, then as for the y value, okay, it is a perpendicular distance, okay, from neutral axis to a point, okay, where the sigma x, okay, and I is the moment of inertia about the neutral axis, right? So this is the basic equation that we are going to use, okay, for the bending stress, right? So if we are to determine the maximum bending stress, so therefore the y value that we are going to use is y maximum. Okay, so then we move on to this sagging and hogging moment effect to the nature of stress, right? So we can see here, okay, if we have a positive bending moment, okay, whereas we can see that this beam will bend downwards, okay, so with positive bending moment, we can see that we are going to have the deformation, okay, of this beam acting in this direction, okay, with the tension zone happening at the bottom and the compression zone happening on top, right? So therefore we can draw the stress block, okay, for this particular beam, okay, which is giving us a negative value of stress on top and a positive a bending stress value at the bottom. Okay, then if we have a negative bending moment, okay, for example, if we have a beam that is a cantilever beam, right? So therefore it will actually bend downwards, right? So but then when we calculate the value of the bending moment, okay, we are going to get a negative value of bending moment, right? So it will bend in this direction. Okay, so therefore, as for this case, okay, we are going to have the compression stress happening at the bottom and the tension stress happening on top, right? As you can see from this red line, okay, is that we can see that this beam actually bends upwards, right? So when it bends upwards, okay, so therefore the top part will be subjected to tension and the bottom part will be subjected to compression, right? So that is why we have two different conditions here, right? So this is for sagging moment and this is for the hogging moment, right? So therefore we can see, okay, that it is already have an exchange, okay, between the compression stress location, okay, and also the tension stress location, right? So as for the top part, okay, it will be subjected to tension, so therefore the value of the bending stress will be positive, and as for the top part, since it is under compression, so therefore the bending stress will be negative.